Hey guys, welcome back here. In this video, we want to take a look at route reflectors. Now, we know that when we're dealing with an iBGP configuration, that we have to have what we would call a full mesh, right? So in an iBGP config, we have to have a full mesh. But when we say full mesh, we don't mean physically connected full mesh, we mean a BGP full mesh. So what we would need to do is we would need to have a BGP peering between 1 and 2, between 1 and 3, and then even if this switch didn't exist, so even if this connection wasn't here, we would have to have a connection through maybe R1 to connect over here to R3. So in reality, you know, the direction of the packets would go like this, but it would form this peering here between R1 and 3 so that we could exchange updates. And the reason we do this is because of the split horizon rule. So let me illustrate what that is. So as R2 sends in a BGP update, okay, so maybe this is for his loopback 1 interface or whatever network he has attached. He sends this over to R1, and R1 says, okay, is the ASN, is the autonomous system number the same? It looks at that. It says, okay, what's the AS that I'm receiving this update from? If it is the same, and that means we have an internal BGP relationship, then R1 is not going to go ahead and send this update out back into the same autonomous system. So R1 is going to stop those updates from ever getting forwarded. That's why we need a full peering. So the only way that R3 would ever be able to reach this loopback would be if R3 had a direct BGP peering with R2 and could receive these updates directly, right? And then that could be through a switch, that could be through another router, that could be anything. You know, if we have reachability via OSPF to our loopback addresses, then, you know, R2 can essentially get to R3's loopback through R1 and form a BGP peering. And so he would go ahead and send those update packets through R1 looking for R3. So we could do that. But the full mesh is kind of a pain in the butt when you have a large deployment of BGP. I mean, some enterprise networks have 30, 40 plus routers, you know, and many more than that running BGP. I've seen networks that are just gigantic and they're all running BGP. To do a full mesh would just be a complete nightmare, okay? And you wouldn't be able to manage it. So you can do a confederation, right? And we looked at that in the confederation video. So that's an option. You can do a confederation. You can do a full mesh, again, if you really want to ruin your life and probably have to find a new job when somebody sees what you've designed. You could do a full mesh, you know, of your 30 or 40 routers. And a small network like this, really, who cares? But the better option is a route reflector, right? Route reflectors can do just what the name implies. They can reflect these routes. So if I have R1, for example, playing the part of a route reflector, what I can do is I can form a peering with all of my route reflector clients to that one device. So R2, 3, 4, and 5, rather than having to form a peering with one another, they would form a peering with R1. This is basically a hub and spoke BGP configuration. I mean, this is a great way to think about it, where you have a hub, this guy would be your hub, and these guys would all be your spokes. Okay, and basically what R1 is going to do is it's going to reflect these updates that come in. So when R2 sends in an update, says, hey, by the way, R1, here's how you get to my loopback 0 interface. What R1 is going to do is he's then going to reflect these updates out towards his route reflector clients. He's also going to reflect it maybe to an external client. So maybe this guy here is an eBGP. Okay, so R1 is also going to go ahead and be able to send those updates out to the external neighbors. Okay, there's some other ground rules there, but I'm not really worried about it at this point. So route reflectors are definitely the easier way to do this. And when we deal with route reflectors, the first attribute that we have to be aware of is going to be the originator ID. So what is that? Well, the originator ID is going to be the 32-bit router ID of where that route came from. Okay, and when we say came from, it could either be the originator or it could be the border router where that route essentially came from. So the easiest thing to remember here is that it's going to be the 32-bit router ID of wherever that route came from. So if if we're talking about, let's say, our loopback 0 here of R3, and R3 sends this update into R1, the originator ID would be the BGP router ID of R3, because R3 would be the originator of this route. However, if R5 sends in an update, and maybe this is eBGP over here, okay, or some other processor or whatever, what have you. Maybe this is OSPF, and we're redistributing, what have you. Once that route enters in to our BGP domain, R3 is going to become that border router of where that autonomous system is. So, keep in mind here, we're running iBGP maybe on our, 2 and 3. And so here's our iBGP autonomous system. So when that route enters into our autonomous system, into our BGP domain, he now becomes the border router. And so once again, even though R3 did not originate maybe the loopback address of R5, the originator ID is still going to be that of R3, okay? And we do this for loop prevention. We do this so that, and I have the debug here so that you can see it, that I can just lecture right off the screen here. It makes my life quicker and easier. So running a debug of all of our updates, you can see that what happens is that R3, the originator ID of a prefix, so maybe 192.168.3.1, which is, by the way, the loopback 1 interface of R1, or R3 rather, the originator of this route, of this prefix, was the BGP router ID. Okay, so the BGP router ID gets attached to this prefix. So now, if R3 ever receives that prefix back, maybe from another route reflector, so maybe R3 sends it up to R1, R1 has a peering with R2, and R2 sends that over to R4. Maybe R4 is another route reflector that R3 might be peering with for redundancy purposes, and maybe that update comes back down from R4. What's going to happen is that R3 is going to look at this and say, okay, what should I do with this? I'm going to deny it. Why am I going to deny it? Because the originator is us. We were the ones that essentially sent that route out to begin with. We were the ones that actually sent out that update to begin with. And so we're going to go ahead and deny it. And it's all based on the originator ID, okay? Now, in route reflector configurations, we also have what's called the cluster list or the cluster ID. So you can see that here in the debug here, the cluster list. What the cluster list is it is a prepended list of cluster IDs that we've gone through. So when we create a route reflector, what's going to happen is that we are going to get what we call a cluster ID, or I just call it a CID. Not really, you can say cluster, whatever you want. So we are going to get a cluster ID on R1. We're also going to get it maybe over on R4. So if we make this guy a route reflector, we're also going to get a cluster ID, okay? Now, you can set this, and I highly recommend that you do so. However, this guy is going to add his cluster ID to the cluster list. This guy is going to add his cluster ID to the cluster list. And the reason why we do this is, again, for loop prevention. So if R4 receives an update and inside of the cluster list he sees his own cluster ID, he's going to go ahead and drop the packet because he knows that that route has already came through him, or he's been involved in some way because he sees his own cluster ID in the cluster list. Now, normally when you have a dual route reflector environment, because let's face it, that's what you want to do, right? So you want to have maybe a route reflector here and a route reflector here, which is probably what we'll do. And then you want to have R3 peer this way, you want to have R2 peer this way, and then these guys will form essentially a virtual peering with one another, right? So these guys, your two route reflectors will be regular peers. You could also make them route reflector clients of one another if you want to, but in this cluster list, it's going to have the same exact cluster ID. So what happens is that as the routes go from one route reflector to another, we can go ahead and drop that packet because we can see that it's already traversed us. But if you have the same cluster ID, we can drop it quicker. We won't have a longer cluster list, right? So let's actually get into our CLI and let's set this up. It's not too big of a deal. Let me just grab this here. So I already have OSPF up and running. Let me actually jot that down in here. This way everybody can understand how this is set up. So we are going to run OSPF. We're going to run process ID 1. Everything is going to be set up in area 0. We do have peerings over the switch. So these guys are point to multi-points. We do have peerings here. We have peerings essentially everywhere that I'm drawing a black dot. So everybody can see one another. Everybody understands how to reach one another. Everybody has a loopback 0, and that's essentially how we're going to form our BGP sessions. So everybody's going to form with the loopback 0, even switch 1 over here. Okay, everybody's going to form with the loopback 0. This guy here, his loopback, all of the router IDs here are going to match the loopback. So loopback 0 for R1 is going to be 1.1.1, 2.2.2. For this guy, it's actually going to be 11.11.11. Okay, the reason for that is it's going to be switch 1, and we already have a 1.1. So let's just go ahead and test reachability here. Make sure we have everything. Show IP OSPF neighbor. So we have a peering with 2 and 3. Let's say show IP route OSPF. We should have all of our routes. Yep, so we can get to 11. Let's say do ping 11. Actually, we'll just copy and paste this. Saves myself absolutely no time whatsoever. Let's say source loopback 0 so we can get to switch 1, because what we want to do is we want to be able to form a peering between R1 and switch 1. Okay, so what we'll do is we'll say R1, R2, 3, and 4 are going to be route reflector clients of R1. Okay, so let's start over here with R1. We'll say router BGP1, BGP router ID 1.1.1. We'll say neighbor 2.2.2, remote autonomous system 1, neighbor 2.2.2, update source L0, neighbor 3.3.3. We could do a peer group here. This would be actually a great opportunity to do a peer group or a template, but it's better sometimes, especially when you're learning, to be able to see all the commands. Okay, we'll go ahead and say redistribute connected as well to make sure that we get do show IP interface brief E assigned. Make sure that we get these 3 loopbacks injected into BGP, the same with our directly connected interfaces, so that we don't break reachability. In case you guys are curious, the reason why I'm not worried about doing redistribute connected is do not forget that the administrative distance of OSPF in this case is going to be 110, and because we are running an iBGP relationship, the administrative distance is going to be 200, so I'm not worried about this network or BGP losing reachability. This is why it's key for you guys to remember things like this to understand when and where you can use different commands. Router ID. So those of you guys that are curious, as I've said in the past, my habit is always to set the router ID. This is one of those occasions where it comes in handy if you set it beforehand. So, and I'll show you what I mean, because we're not going to set up the route reflector clients first. So do show run section router BGP. We're going to set them up after we have a peering. And if I set the router ID after that, it's going to cause my peering to bounce, even though setting up the cluster will, the route reflector will also cause that. You know, the point is that we want to try to form, we want to try to cause at least damage as possible, right? So we're going to say update source, loopback 0, redistribute, connected. All right, so we have a peering here. Do show run section router BGP. Let's go over to R3, router BGP 1. Let me just say do show IP route OSPF. Good, okay. So we'll say router BGP 1, BGP router ID 3.3.3, neighbor 1.1.1, remote autonomous system 1, neighbor 1.1.1, update source L0, redistribute, connected. So if we head over to R2, do show IP BGP, let's see what we are getting here. So we're not getting the 3 interfaces over on 3 yet. Do show IP BGP summary. Do show IP BGP. We're not getting anything yet. Do show IP interface brief E assigned. What we're looking for is we're looking for these 3 loopbacks. Every router is going to have the same 3 loopbacks. So loopback 1, 2, and 3. So let's just give this a minute here. We haven't gotten anything from 1 yet. We've gotten 7 from, let's take a look. Okay, so R1 at least has the 3 loopback addresses from R3. But we'll notice that over on R2, we don't have them. And the reason is because of this split horizon rule. So what we're going to do is we're going to make R1 a route reflector. We're going to tell R1, listen, I want you to be able to reflect these routes. But let's also throw R4 and R5 into the mix. Do shall run section router BGP. So let's just go ahead and we'll copy this. We'll say 5.5.5 and remote AS1. Neighbor 5.5.5, update source, loopback 0, and we're going to go ahead and loop in 4.4 as well. And the reason why we're going to do this, guys, is because we're not going to make R5 a route reflector just to see what happens. I mean, a route reflector client just to see what happens. So here at this point, we have direct peerings with R2, R3, R4, and R5. And, you know, while we're here, we might as well just go ahead and add switch 1. So we'll say remote AS1, and then neighbor 11.11.11, and we'll say update source loopback 0. All right, so there's our configuration. Let's go over to 4, router BGP1, BGP router ID 4.4.4, neighbor 1.1.1, remote 1, neighbor 1.1.1, update loopback 0, redistribute connected. Over to 5, router ID 5.5.5, neighbor 1.1.1, remote 1, neighbor 1.1.1, update L0, redistribute connected. Okay, so let's say do show iBGP, and you can see that we're getting the 3 loopback addresses from R1, but we're not getting them from anybody else. In other words, we're not getting any of the other routes that R3 currently has. And the reason is because we have the split horizon rule. So let's go ahead on R1. What we're going to do is we're going to go ahead and say that R2, 3, and 4 are route reflector clients. We're not going to do that with switch 1, because switch 1 is actually going to become a route reflector client as well, because we're going to form a cluster there. So let's go ahead and say do show run section router BGP. The only thing we're going to have to do here is say neighbor 2.2.2 route reflector client, and then we'll go ahead and say neighbor 3.3.3. You can see that our adjacency does bounce, and that's okay. So we'll go ahead and pop this in. We need to do the same thing with neighbor 4, and we're going to do the same thing with neighbor 5. We won't do it again with 11, with switch 1 rather. So we'll say route reflector client. Now again, you can see how much typing I've done. You can see all the different commands here. So here's essentially my route reflector client commands per neighbor. You know, great example of where we could use a template or a peer group. This would have saved us a lot of typing. If we just set up a peer group, we would essentially have needed 3 commands in the peer group, and then simply to add the neighbors to the peer group. So we would have had a lot less commands there. Actually, I messed up here because I said we were not going to do this to R5, and we did it anyway. So let's go to R5, and we'll say do clear iBGP star, and just clear the peering. So here we have R1. Let me say do show iBGP, and let's actually take a look at what we have. So we have all these routes coming in. So 192.168, 1, 2, 3, 4, and 5. And let's take a look at 2. Let's see what he has. Let's say do show iBGP, and you can see that now we have not only the addresses from 3, but 4 and 5 as well. If we check 2, or if we check 4 rather, here was what we originally had. Let's say do show iBGP now, and now you can see we have the 1s, the 2s, the 3s, the 4s, and the 5s. Let's check R5. Do show iBGP, you can see that we have the same thing. So 1, 2, 3, 4, and 5. So you can see that even though R5 is not a route reflector client, he is now getting those routes reflected, even though he's now not a route reflector client, and that's because R1 is a route reflector, and he's gone ahead and said that these clients here, R2, 3, and 4, when he receives a route from a route reflector client, he will go ahead and reflect those routes to non-reflector clients. So in the beginning of the video, you know, I kind of mentioned there are some other ground rules. Well, that is one of them. So being that 2, 3, and 4 are route reflector clients, R5 is now getting those addresses that have come in from route reflector clients. So that's why R5 gets them, even though he's not a client. Okay, so do show run section router BGP. Let's go, and we've examined the config. Let's actually pick one of these. Let's say do show iBGP, and let's actually pick this prefix here. Do show iBGP, and pick this prefix, and let's see what we have here. So let's pick another one. Actually, I don't know why I picked my own. We'll say 3.1/32. You can see that we have the originator and the cluster list. So from our force perspective, the originator of this route was whatever device has the router ID of 3333, which we know because we set our router ID as router 3. You can see here we have the cluster list, and here is the cluster ID of the route reflector where it came from. Okay, so when we have a route reflector implemented, we're going to see these 2 different attributes added to our BGP table when we take a look at the prefix. Okay, now let's go ahead and let's actually make switch 1 a route reflector as well. So what we're going to do is we are going to say config t router BGP 1 BGP router ID 11.11.11.11, and we're going to say neighbor 1.1.1, remote 1, neighbor 1.1.1, update source, L0, and we're going to say redistribute connected. So at this point, what we're going to do is we're going to peer our route reflectors together. So do show iBGP summary. We are going to peer R1 with switch 11. So if I say do show iBGP, you can see that I'm getting all of the, and check this out, this is the cool thing. You can see that I'm getting all of the addresses that came in from route reflector clients except for R5, because R5 was not configured as a route reflector client. Okay, so R5 is kind of this redheaded stepchild that I just wanted to use to demonstrate that. So what we'll do, let's say do show run section router BGP. What we can do is actually just grab this entire configuration up to R4, and we can go ahead and pop this in on switch 1. All right, because R1 and switch 1 are going to go ahead and form a peering to be able to exchange updates between one another, and then we will go ahead and we will have have peerings between these guys and have dual route reflectors. So let's go to R2, and all we need to do is say neighbor 11.11.11.11, and we'll say remote 0 and update source L0. What we'll do is we can go and grab, we should still be in that config, so we can just grab this, go to 3, pop that in, and pop in the update source. And R4, same thing, so we can go in, we can grab the same thing. Remember, we're not going to do this on 5, because at this point, you know, our use for 5 has been demonstrated, so we're good to go here. So our switch 1, so we have peerings with 2, 3, and 4. So let's say do show iBGP summary and actually see what we have. So we have a peering with 2, 3, and 4. We're receiving 7 prefixes. Let's say do show iBGP. And let's see what we have here. So we are getting all of these updates in. So let's go down switch 3 here for a minute. Let's say show iBGP. Let's see what we are getting in. And let's take a look at, we need to pick a good prefix here. Let's take a look at the ones that are coming in from 2. Okay, so you can see here that in this particular case, we are now receiving this this particular address here from R1. We are now receiving it from 11.11.11. So we're now receiving this from switch 11. Okay, or switch 1 rather. Okay, and you can see the cluster list here is changed to 11.11. So it's actually changing to switch 1. All right, now, if we pick a few others here, let's say show iBGP, and let's actually scroll down here. So let's say show iBGP and take a look at maybe this prefix here. Let's see where this is coming from. Same thing. So we can see that we have 2, right? We can see that this one came from the cluster list. This guy was originated by 4.4.4. The cluster list here was 11. The cluster list here rather was 1. The cluster list here was 11. So we see that we are getting 2 different cluster IDs. Now what we can do here is we can go into switch 1, and I can say BGP cluster ID, and I can set this to a specific cluster ID. So I can say 0.0.0. Maybe 1. And I'll go ahead and I'll do the same thing. You can see that it's going to go ahead and reset the peerings. I can go ahead and create a route reflector cluster now between R1 and switch 11, and you can see, or switch, I keep saying switch 11, switch 1, and you can see now that we have this peering that just came back up. It just reset. Do show iBGP summary, and now I have a route reflector cluster between R1 and R11. So I can go back here and say show iBGP, and you can see now that I'm receiving the routes from the same cluster ID. So now in the cluster list, I'm not going to have a prepended list of cluster IDs, because now it's essentially coming from the same cluster. So if I lose R1, so let me say neighbor 3.3.3 shut. Actually, who's my best path here? So it's R1. So you can see here that it's coming from R1, and that is best. So let's go ahead on R1 and let's shut this guy down. And then on R3, let's actually take a look at this update again. You can see that now I'm still getting the route to R4's loopback address, but now I'm getting it through the second route reflector, which has now become my best. If I go in and unshut this, we'll no shut this, we'll let the peering come back up. We'll go to R3, and now you can see that it comes back, and R1 has now become, again, my best path. Okay, now you're still going to have best path selection, and I'm not getting into that. I'm not going to go through that. We already have a whole video series on the best path selection. But the point is to show you guys that now you can have these cluster IDs, and you can prevent, if you don't set up a cluster ID in some configurations, you can hurt yourself, because you may actually find that you may end up causing a loop in your network. The best thing to do when you configure a route reflector, you're going to always configure more than one, unless you have a very, very small network, is to set the cluster ID to some 32-bit number so that they're the same and that you don't ever worry about, traversing different route reflectors and causing a problem. So always set the cluster ID. It's my recommendation. But here's how we set up these route reflectors and dual route reflectors inside of our network.